a lot of the definitions of that.
So maybe like
guessing
maybe like the persistence of the ridge, whether it becomes a block, persists. It tells you something about the magnitude of the warming that ends up happening.
Yeah, I think so. And I think if it's anything similar to this event, you probably need some cooling to happen beforehand.
Right. Yeah, to like get that
Kinda
spread.
enhance that. Yeah, exactly.
Yeah, cool. Nice.
And practice.
Yeah, right, yeah.
Yeah.
You might get asked the exact same question by somebody else, so now you've practiced the answer, and now you're good.
Appreciate it.
Yeah.
Well, welcome everybody. I am not John Martin. I'm not. No, I'm Pete. John is in. This is Dave. John is Dave's advisor, and John is in Miami, but through the magic of television, John is going to introduce Dave.
Good afternoon. It's my pleasure to introduce today's speaker, Mr. Dave Mikolajczyk, who is nearing completion of his MS degree here in the department. Dave hails from Apple Valley, Minnesota, and graduated with his BS from our department in May of 2012. And upon finishing his degree, he went to work in the Antarctic Meteorological Research Center and has made several trips to the continent in that capacity. And naturally, that means he could fill at least 2 seminars with tales of adventure on the ice. And it's really too bad that we don't have time for that. But a couple of years ago, Dave approached me about working on his master's degree. And it was during those first couple of meetings that he introduced me to the occurrence of extreme warming events in winter. These phenomena immediately caught my attention. I didn't know they existed. So he began thinking about a thesis plan. And eventually we thought a thorough case study of one such event might be a good way to gain understanding of the physical processes that drive these incredible events. And so he set off on that road. Now, among the many challenges the work forced upon me was the struggle of learning how to view weather systems and their processes from a southern hemisphere perspective. You'd think it'd be easy, but it rather reminded me of the problem of looking the wrong way while attempting to cross the road in Britain, but with substantially less dire consequences in the face of error. How remarkably prescient that his work on understanding the physical factors that underlie such events would be nearing its completion, nearly coincident with a high-profile temperature record recently observed in East Antarctica. Well, Dave's most recent trip to the ice this past fall and winter involved more than his usual set of tasks, as he was also determined to write his master's thesis through adoption of a hermit-like existence on the big ice. He definitely succeeded in that task, and today he's going to tell us about a regional warming event in winter on the Ross Ice Shelf, Antarctica, as observed by UW-Madison automatic weather stations. So take it away, Dave.
All right, well, thank you for that, John. Can everyone hear me everywhere? Sweet. All right, awesome. So, as John said, I'll be talking about a regional warming event that occurred in Antarctica as observed by the Automatic Weather Station Network on the Ross Ice Shelf, Antarctica. So, here's an outline of what I'll be talking about today. First, I'll go over the definition of what a regional warming event in winter is, so then we're all kind of on the same page and all can kind of be thinking about that as I go through the talk. Then I'll go over a little bit of background about the Antarctic meteorology and climatology, to get everyone introduced to that in case you weren't too familiar with the region. Then I'll go over the data and methodology that I used for this study, go over the case study analysis of the regional warming event, talk about the results of that and discuss it a little bit, and then go over some conclusions and future work. So first, the definition of a regional warming event. We'll go over that. So a warming event is defined as one automatic weather station observing an increase in temperature of greater than 30 degrees Celsius in 5 or fewer days. And to be regional, more than one of those automatic weather stations needs to observe a warming event at the same region at about the same time. And so from the 12th to the 15th of July in 2007, a regional warming event was observed on the Ross Ice Shelf, Antarctica. So spoiler alert, this is actually what the data looked like. And so I wanted to show this so then you can get a little visual representation of what this warming event looked like. So this is plots of 14 automatic weather stations. And the one I'll just kind of point out quickly here is on the upper left, that's the plot of temperature. And it's showing data from the 10th through the 17th of July. and it's showing temperatures in degrees Celsius from -60 up to 0. And so in general, we see a general cooling trend and then a rapid, steady increase in temperature. I'll use the pointer actually, maybe it'll be a little better. General cooling trend and then a rapid increase in temperature of upwards of 40 degrees Celsius in a pretty quick amount of time, a couple days. And so, yeah, just keep that in mind, and then we'll go into why that actually happened, what the whole environment kind of looked like to lead to that event. So first, if you're unfamiliar, Antarctica is a continent of extremes. It's on average the highest, driest, windiest, and coldest continent on the planet. And these plots are showing elevation of the continent. So it's composed primarily of a big dome of ice and snow. And on the right-hand side, in East Antarctica, some of the elevations get to about 4 kilometers above sea level. In West Antarctica, it gets about half as high, maybe a couple kilometers above sea level. And in between West Antarctica and East Antarctica is the Ross Ice Shelf. And the Transantarctic mountain range kind of splits the continent in two. And so the ice and snow is flowing off of the continent and onto the surrounding seas and forming these large ice shelves. And these ice shelves are floating at about sea level, and on the Ross Ice Shelf is where a lot of the automatic weather stations are located. So to go over a little bit of the temperature regime of Antarctica, when considering the monthly mean temperatures, in general the temperature trend has been known as having a coreless winter. And so that is basically where the monthly average temperatures drop sharply in autumn and stay relatively uniform and cold throughout the winter months, and then increase sharply again in spring. So the graph on the right kind of depicts that. As you see, instead of a typical sinusoidal wave, you see a kind of a sharp drop and then a flat bottom during the winter months, and then a sharp increase again. And one interesting note is some little increases in the monthly mean temperature at some locations. And so these increases in temperature have been attributed partly due to rapid and intense increases. The increases in the monthly mean temperatures have been associated with rapid increases in temperature, and that's due to various reasons throughout the continent. But when we focus on the Ross Ice Shelf, one of the main reasons that the surface temperatures increase is due to cyclonic activity. And so there's been some studies that have investigated just upstream of the Ross Ice Shelf, just off the coast of Adelie Land. That region is a known region of active cyclogenesis. And so that cyclones can form off of the Adelie Land Coast, propagate eastward into a region, a climatological known region of surface low pressure system location, and that's known as the Amundsen Sea Low. And especially in the winter months, the Amundsen Sea Low is just situated north of the Ross Ice Shelf. And so the interaction between the active cyclogenesis off the Adelie Land Coast and the location of the Amundsen Sea Low has an impact on the atmospheric circulation, particularly in the Ross Ice Shelf region. Going a little bit further in depth on the Ross Ice Shelf climatology, some studies have used, like the one in particular, Costanza et al. 2016, have used automatic weather station data to classify the climatology across the Ross Ice Shelf. And so the plot on the right is showing average resulted wind vectors, and so the length of the arrow is the strength of the wind, and it corresponds also to the direction. And so the Ross Ice Shelf is bordered by the Transantarctic Mountains on its west, and so in this plot, the South Pole is at the top. So to its west, the Transantarctic Mountains border the Ross Ice Shelf. To its east is West Antarctica. And at the southern end of the Ross Ice Shelf and along the Transantarctic Mountains is a known region of strong low-level winds known as the Ross Airstream. So in the southern end, along the Transantarctic Mountains on the Ross Ice Shelf, that's generally a windy and warm, relatively windy, relatively warm location. In the center of the Ross Ice Shelf, that's calm and cold. And at the northern end of the Ross Ice Shelf, the lowest pressures have been found there. So in considering all these different aspects of the meteorology and climatology of Antarctica, we can use those to start to investigate what mechanisms caused this regional warming event. We'll look at how the temperature and wind patterns evolved over the Ross Ice Shelf and how the large-scale meteorological environment evolved before, during, and after the event. And so we'll use automatic weather station observations and reanalysis data to investigate this. So next I'll go into data and methodology. So we'll analyze the meteorological environment before, during, and after. We will look at the significance of the warming event by comparing automatic weather station climatologies to, or observations during the event to their climatologies. And we'll look at the large-scale anomalies and how those patterns deviated from normal. So this map shows all of the automatic weather stations that were installed on the Ross Ice Shelf in 2007. There were all the black dots mark their locations. There were 19 total at that time. And so I looked at all the temperature data in July of 2007 at each of these sites and counted up how many observed a warming event. And so this is an example of one location, Schwerdtfeger AWS. And so that's kind of on the, and then I'll go back to this plot, in the center of the ice shelf and kind of near the Transantarctic Mountains. And so this is a plot of temperatures at Schwerdtfeger. On the top, the plot is showing the whole month of July. And just kind of looking at it broadly, you can see that there's a really sharp increase in temperature in the middle of the month. And that is when the warming event occurred. Leading up to that event, in the days before it, there's a general cooling trend. The warming event happened, and then the general cooling trend continued. The plot on the bottom just shows a zoomed-in view of the temperature observations there. The black vertical lines mark the beginning and the ending of the warming event. So the data I used in this study were automatic weather station observational data of temperature, pressure, wind speed, and direction. I looked at ERA interim and ERA 5 reanalysis output. I used them kind of interchangeably. I know there are some differences, but for the most part, they represented the atmospheric patterns relatively reliably well during this event. I looked at infrared satellite composite imagery to get a sense of where the large-scale low-pressure systems and cloud cover were located during the event. And I looked at CloudSat Calypso satellite data retrievals to get a more in-depth sense of the cloud cover and its impact on any radiative impacts that it had over the Ross Ice Shelf. So now I'll go over a case study analysis of this event. And so first I'll show the automatic weather station observations during the warming, and then go over some reanalysis data at 3 time steps. Rather than going through the whole thing, I'll just show some highlights and some specific elements of the environment that I want to point out. So there were 14 automatic weather stations that observed warming during the event. This map here shows all of the locations that observed warming, and the dots are colored by the onset of the warming. So the lighter the color, the earlier the warming event started. And so in general, the warming started on the left-hand side of the Ross Ice Shelf, so that's in the eastern side of the Ross Ice Shelf, and then progressed to the right, or progressed westward. So I will be focused, And so these are all once again, here are all the observations. So in the upper left is temperature, the upper right is pressure in hectopascals, the lower left is wind speed in meters per second, and the lower right is wind direction in degrees. So, as I had mentioned before, there was a general cooling trend before the warming event happened. Pressures were generally pretty steady. Wind speeds were pretty calm, generally between 2.5 to 5 meters per second. And the wind directions were fairly sporadic, nothing too dramatic to see there. But as the warming event happened, the temperatures started to increase and the pressures started to decrease, pretty much a 1-to-1 relationship. Also, the wind speeds in general at most of the sites increased, mostly especially at the beginning of the event, and sometimes the wind speeds kind of varied throughout the event depending on the location. And for a lot of the sites, the wind direction became more constant during the warming event. So I'll focus on Elaine AWS, and I'll go back just to point that out specifically. Elaine AWS was the first warming event, first station to observe a warming event, and that's located on the southern end of the Ross Ice Shelf near the Transantarctic Mountains. So Elaine's warming event began at 6:10 UTC on 12 July, ended at 22:10 UTC on the 14th, and the temperature was -47.2 Celsius to start, warmed to -7.9, which was a 39.3 degrees Celsius increase in about 2.5 days. Next, I'll go over some reanalysis data during this event to see how the meteorological environment evolved. So first, this is kind of a general schematic of some things that I'm going to point out in these next few plots. And so this is showing, in the color fill pattern, it's showing 2-meter temperatures. And this is a plot at 0Z 10 July, so a couple days before the warming event began. And so we'll be looking at a region of active cyclogenesis that just off the Adelie Land Coast. Also, I'll note that there was a pretty stationary low pressure system in the northern Ross Sea in the days leading up to the event. Downstream of that stationary low was a large ridge, and in between the two was warm northerly flow that was advecting warm air southward towards the west Antarctic coast. Over the Ross Ice Shelf, there were pretty calm conditions. A cold pool developed, and due to these calm conditions and the strong northerly flow here, a large temperature gradient, or a strong baroclinic zone was established just north of the west Antarctic coast. And it, throughout the days leading up to the event, it kind of just kept maintaining its strength, stayed in approximately that location, and then we'll see how things evolve in a second. So these plots show on the top 850 hectopascal geopotential height, winds, temperature, and relative vorticity. So the heights are in the black contours, winds are the wind barbs, the temperature is the red dashed contours, and the relative vorticity is only the cyclonic relative vorticity, so negative in the southern hemisphere, color-filled purple. On the bottom is showing variables near the surface, so mean sea level pressure in the black contours, winds, and 2-meter temperatures in the red dashed contours. And the L's, I put that in myself, did a little bit of analysis, and said, all right, here's where the lows are, just kind of help you watch the lows move throughout the time steps. So at 850 hectopascals, there's a low that was located, and especially prevalent at the surface, just north of the Adelie Land Coast. And so the surface cyclone is much more well-defined in the mean sea level pressure as opposed to 850 hectopascals, just by looking at the broad region of geopotential height minimums in that area. Upstream of that, in the northern Ross Sea, there is a co-located low at 850 and at the surface. And downstream of that low is the warm northerly flow that has set up a strong baroclinic zone seen by the tightly packed isotherms that stretch from the location of the stationary low towards the west Antarctic coast. And so the atmospheric conditions over the Ross Ice Shelf in general are pretty calm, just as owing to the fact of the spread out mean sea level pressure and geopotential height contours at this time. Also note the isotherms at just off the Adelie Land Coast. Note how they're kind of tightly packed but a little spread out. If we advance one day ahead, and so now we're at 12 UTC on 11 July, those isotherms are a little more tightly packed, and there's a little more bending of the isotherms due to the stronger low that was located off the Adelie Land Coast at this time. So that stronger low at 850 millibars also has better upper level support at 500 and 300 hectopascals. And it's also a deeper and more tightly packed low at the surface. So I'll just kind of go back and forth for a couple of steps here. And so note that the low at 12Z 10 July had progressed eastward into the Ross Sea, but the Ross Sea cyclone didn't really move much. It kind of remained in the same location and actually decreased in strength a little bit, just looking at the sea level pressure minimums going from sub 976 hectopascals to sub 980. So that the low that propagated eastward off of the Adelie Land Coast didn't really do much to the stationary low in the Ross Sea at this time. But this stronger low at 12Z on 11 July will eventually have better upper level support, better barotropic support, propagated eastward, merged with the stationary cyclone in the Ross Sea, and then now I jumped into the middle of the warming event, and that cyclone in the Ross Sea strengthened and moved quickly southward towards the Ross Ice Shelf. As it moved southward, it reoriented this baroclinic zone that had been developed off the north of the West Antarctic coast and brought it into a more meridional orientation, especially evident here at 850 hectopascals, and swept it across the Ross Ice Shelf from east to west. So now we'll go into a little bit more in depth on what happened during this warming event, and we'll look at the upper level 500 hectopascal geopotential height anomalies and how they relate to the 2-meter temperature anomalies. Then we'll look at the development of the cold pool, the cyclogenesis off the Adelie Land Coast, and the progression of the warm front across the Ross Ice Shelf. So we'll kind of do a before, during, and after look at composite geopotential height anomalies at 500 hectopascals and composite mean sea level pressure and 2-meter temperature anomalies. So the plot on the left is showing the 500 hectopascal anomalies, and this is a composite from the 5 days before the event began, so the 7th to the 11th of July. And these are relative to the July 1981 to 2010 climatology. So there is a geopotential height minimum anomalous low in the Ross Sea and a strong anomalous ridge with strong positive anomalies downstream just north of West Antarctica, and then another low east of South America, and relatively stagnant, I guess, geopotential height anomalies over the Ross Ice Shelf. And looking at the surface, the composite mean sea level pressure shows a broad area of low surface pressure in the northern Ross Sea, approximately co-located with the geopotential height anomaly minimum at 500 hectopascals. Downstream of that is a broad composite ridge that also shows the northerly flow and strong region of anomalously warm 2-meter temperatures just off the West Antarctic coast and over West Antarctica. And so this suggests that this low for the first 5 days or so before the event began was relatively stationary in the Ross Sea, and there was a broad region of ridging downstream of that. Then looking at these same data, but during the event, so composited from the 12th to the 15th of July, I'll call it a wave train right now, but I don't know if that's technically what it is, but still this line of anomalously low heights to high to low that was around West Antarctica shifted a little bit more towards Antarctica, and the anomalous low in the Ross Sea shifted southward and deepened. The anomalous ridge near West Antarctica weakened a little bit, but shifted more towards West Antarctica, and that positioning helped to bring the warm northerly flow closer to the Ross Ice Shelf region. Looking at the surface, the composite mean sea level pressure shows the progression of the cyclone towards the Ross Ice Shelf and the continued northerly flow upstream of that, and now the region of anomalously warm 2-meter temperatures has moved over the Ross Ice Shelf. After the event ended, from the 16th to the 20th, the composite geopotential height anomalies show that wave train pattern is kind of gone away, and now instead there's more of a dipole set up in the Ross Sea and Ross Ice Shelf regions, with an anomalous low in the northern Ross Sea and an anomalous ridge over the Ross Ice Shelf. And there's a broad region of mean sea level pressure minimum over the Ross Ice Shelf that reflects the movement of the energy away from the Ross Ice Shelf as the cyclone weakened. Temperature still remains a little bit anomalously warm as the atmospheric pattern started to calm and just kind of slowly start to cool again. So now we'll talk about the development of the cold pool and a strong surface temperature inversion that happened over the Ross Ice Shelf. So to do this, we'll look at CloudSat Calypso satellite data retrievals. And so these satellites are polar orbiting satellites, and they measure data at a pretty fine horizontal spatial scale, but they get good vertical profiles of different variables. And so the plot on the left is showing the path of these two satellites. And so it's going from the northern latitudes over the Amundsen Sea, southward over the Ross Ice Shelf. And so the plot on the right, the left side is the northern regions, and the right side is over the continent. So looking at the cloud phase panel so panel B here, that is showing whether it's colored by whether it's ice, which is red, or mixed phase, or liquid. So most of these clouds are ice phase clouds, and there's a deep region of cloudiness approximately around between locations B and C that I've marked here. And so that's about in the region where there's the northerly flow and where the baroclinic zone was established. And with this deep cloud cover, there's a lot of reflectivity shown. There's a lot of precipitation happening, and some of the strongest downwelling long-wave radiation in this location, as well as with the low cloud cover and fog just north of that. Looking at the Ecmwf temperatures, the vertical profile of the temperatures here, in general, there's a big warm pool just on the northern side of this cloudiness, and then in general, it's cooler as you move southward over the Ross Ice Shelf. Looking back at the cloud phase there, it indicates that there's some low cloud cover there over the Ross Ice Shelf, but it's fairly thin, as suggested by the low values of downwelling long-wave radiation. The bottom of the atmosphere long-wave cloud radiative effect just kind of gives you a sense of what the radiative effect is at the actual surface. And so this is just kind of shown so we can actually see what the values are. And in general, there's more radiative effect, long-wave radiative effect in the northern portions of this satellite retrieval, and a little bit less so of the Ross Ice Shelf. This is, and so this will go back. These data were recorded at 9:40 UTC on 10 July, so a couple of days before the warming event began. And then a few hours after that at 12 Z, 10 July. This is the infrared satellite composite image. So this is confirming that cloud cover that we see in the satellite data retrievals. This is in the region of warm northerly flow, establishment of that baroclinic zone around point C, and over the Ross Ice Shelf, not too much in the way of cloud cover that we can really glean from this satellite image. Of course, with the data retrievals that indicated low cloud cover, which could kind of get kind of difficult to see at times over the cold Ross Ice Shelf. So this is a plot of the temperature observations at Adelie Land in red, spanning from the 10th of July to the 17th of July, and Era 5 10-meter winds in blue dots. And so, as we've noted before, there's a general cooling trend. Oh, also I'll mention, the black horizontal lines mark the climatological mean temperature at Adelie for the month of July. So that's approximately negative 32 degrees C, as well as 1 and 2 standard deviations above and below the mean. So as we've moved towards the beginning of the warming event at Adelie Land, temperatures cooled from a little bit above the mean July temperature at Adelie Land to just cooler than 1 standard deviation below the mean. Then the warming event began, and temperatures reached to above 2 standard deviations above the means. Temperatures got pretty anomalously warm at Adelie Land. At the same time, the winds, the Air 5 10-meter wind speeds show that in general the winds were pretty calm, around 2 to 5 meters per second before the warming event began. As it began, the wind speeds increased up to from about 2 meters per second up to 5, stayed steady throughout the warming event, and then increased again at the end. We got pretty high to almost 15 meters per second just after the event ended. So this shows a vertical temperature profile at Adelie Land, and this is at the beginning of the warming event, and this is really interesting because it shows an extreme surface temperature inversion that has been established just before the warming event began. And so to get a sense of the strength of this inversion, at the model level surface, which is at 1,002 hectopascals, the temperature was negative 45.1 degrees Celsius. At the next model level up, where the surface inversion ended, the temperature was, I should say, negative 28.3 degrees Celsius, a difference of 16.8 degrees Celsius, which is extreme. And above 975 hectopascals, the temperature is generally cool, up to 400 hectopascals in this plot. But to note, that difference of 16.8 is obviously not 30 degrees Celsius. So this warming event was not caused, this tells us, or suggests anyways, that this warming event wasn't caused only by mixing out of this strong surface temperature inversion that occurred. There must have been something else that led to this, or that contributed to this warming event. Also note that the wind speeds throughout the whole column here are generally calm before the warming event began. Next, we'll talk about the cyclogenesis off the Adelie Land Coast. So here are a couple plots, again, before the warming event began. The left is showing 12 UTC 10 July, the right is showing 12 UTC 11 July, same times that I had talked about before. Slight difference in what's plotted here on these ones, though. The black contours are now mean sea level pressure, but the fill patterns are the 850 hectopascal relative vorticity. And so the main thing that I want to point, main two things I want to point out here is that there's a difference in collocation between these features at these different times. So on 10 July, the minimum in sea level pressure is not located in the same region as the maximum in relative 850 relative vorticity, whereas at 12Z 11 July, those two features are pretty much co-located. And so that is a representation of the lack of upper level barotropic support at 10 July for this cyclone here, for it to propagate with enough strength eastward to have any noticeable effect on the stationary cyclone in the Ross Sea, whereas the cyclone on 11 July was much stronger. Now we'll talk quickly about the progression of the warm front across the Ross ice shelf. And so one thing in the classical sense that we need to have in order to have a front is to have a region of larger than background temperature contrast, larger than background static stability, and larger than background relative vorticity. Did I get those right? I should have wrote that down. But anyways, this plot here is showing the 850 hectopascal geopotential heights, relative vorticity, and temperatures and winds over the Ross ice shelf in the middle of the event. And this is, we got 2 out of 3 right here. We got larger than background relative vorticity and a large temperature gradient shown by the isotherms here, tightly packed together in the middle of the Ross ice shelf. This is in the middle of the event. It's also, you also can see a signature of a trough in the geopotential heights here as this warming event progressed from east to west. And looking at the vertical temperature profile at Adelie Land and its evolution over time, from before the event began to through the event and after. In general, the temperatures throughout the whole column at Adelie Land didn't change much before the event began, but during the event, you can see a signature of a higher static stability, especially in the middle portion of the atmosphere as this front progressed along Adelie Land. So quickly I'll show the satellite data retrieval, the Calypso satellite data retrievals in the middle of the warming event as well. So these are at 7:39 UTC on the 14th of July. And this is just confirming what we had figured, that there's more cloud cover now over the Ross Ice Shelf in the middle of this event. That's contributing to some downwelling long-wave radiation over the ice shelf. The path again is this red line here, going from left to right across the middle of the ice shelf. And now there's a big warm pool over the whole ice shelf, and especially warm temperatures on the eastern side. And here again is the satellite composite image at approximately the same time, showing that cloud cover over the Ross Ice Shelf, especially high cloud cover in the eastern portion. And the vertical temperature profile at Elaine at the end of the event shows general warming throughout the whole column. The surface temperature inversion is pretty much eroded. This is a little bit after the event ended, so maybe that's why you have a little bit of signal of the inversion coming back again. But the wind speeds throughout that whole column have increased, and they're now backing with height, which is indicative of warm air advection at this location. So, in conclusion, we found that prior to the event, there was a stationary 500 hectopascal wave train that led to a buildup of warm air just north of the west Antarctic coast and north of the Ross Ice Shelf. The calm and atmospheric conditions of the Ross Ice Shelf led to a large cold pool developing with strong surface temperature inversion. And a cyclone off the Adelie Land Coast progressed eastward and merged with the stationary Ross cyclone in the Ross Sea, led to its strengthening and southward propagation. And there's a warm frontal passage across the Ross Ice Shelf from that cyclone that eroded the cold pool by way of, looks like, several mechanisms. One, so that's not, that alone wasn't enough to account for the warming. There's warm air advection and cloud cover, and increased winds, which is a representation of an enhancement of the Ross airstream. So some future work would be to investigate how this wave train was established, whether there was any tropical connections that led to it, and then better quantify the contributions of the various factors of the warming. So look at the role of warm air advection, better quantify the turbulent mixing out of the inversion, and look at possible adiabatic warming from katabatic winds from the outflow or the downslope flow from east and west Antarctica, and look at the long wave radiated feedback from the cloud cover and get a better sense of the surface energy budget. Here are all my references, but I won't go through those. So I would like to thank a lot of people for all this research. First, to Linda Keller and Matthew Zara for introducing me to this topic many years ago, when I was an undergrad, actually. That's fun. And also thank you to John Martin for piquing my interest in synoptic meteorology and being an awesome advisor. Thanks to my committee, Tristan and Stephanie, for their support. And thanks to the High Impact Weather Group for all your fun meetings and discussions on anything and everything. Thanks to Ellen for those awesome CloudSat Calypso plots. And thanks to everyone at AOS and SSEC for all their support. Thank you to my partner Chrissy for helping me out, especially in these last little bits of this presentation. And thanks to all my family and friends for all their love and support. So thank you. I suppose we'll take questions too if anyone has them.
I do have a question from John, but if there's any students that have questions, I'll let them go first.
Yeah.
I'm not super familiar with the topic, but I was wondering how wide those temperature inversions are. Like, is it just really close to the ground, or how far up do they go?
Oh yeah, they are really close to the ground. Yeah, this model level, I think, should have written it down, but I think it's like 20 or 30 meters above the surface where the temperature then starts to cool again.
And
So, yeah.
do you think if you have those sorts of inversions often, do you think that would lead to an overstatement of like large anomalies, like when the inversion does get destroyed? Suddenly you see something that's much warmer, even though there's only that little bit of air that actually got that much warmer.
Yeah, maybe, but like if you just mix out the inversion alone, you might get like, as was seen here, like a 15 to 20 degree, about a 15 degree Celsius increase in temperature pretty rapidly. But to get anything greater than that, it seems like you need a larger scale, or you need another mechanism to help that warming get to those large increases.
I guess, I don't know how related it is, but I'm thinking about what I've been seeing in the news the last few days. We see like a 30 degrees Celsius warming.
Yeah.
And it's like, is a lot of that just the surface temperature?
Yeah, I think it depends on where you are on the continent. So I think over the Ross Ice Shelf, the surface temperature inversion really helps with that. Over East Antarctica and the East Antarctic Plateau, when you get to those higher elevations, I'm guessing that some of the surface temperature inversion set up in the calm atmospheric conditions beforehand helped, but also in the case that happened a couple days ago, there was a persistent ridge and warm northerly flow cloud cover that kept on happening. So I'm guessing that with that case, and maybe others, to get to such a large temperature increase, you just need to have a really persistent flow and just have it kind of stationary there, and just keep on coming to advect some warm air of the region.
Thank you.
Yep. Terry, that's how you come up.
Yeah, so I know that the Calypso, they have 5 kilometer level 2 products. I was curious what the resolution of your CloudSat Calypso merge product is, and if it's very narrow, do you have plans to kind of use some passive imagers to kind of better characterize the cloud fraction and optical depth of field?
Yeah, I don't recall what the swath width is, or the path width is for these data. The top of my head, I feel like it's 12 kilometers, but yeah, I can't recall exactly. It would be great to use more data to get a better sense of the actual cloud cover here. And I think you'd kind of need to at least have some of that in situ data to get a better, accurate calculation of the what clouds are there and how they contributed to the surface energy budget. I saw Brad's hand up next, yeah.
I think you made a very convincing argument about the role of the synoptic transport, and I like that at the end you suggested the input kind of with how would you go about trying to diagnose what those kind of winds are?
So, I think to do that, well, I think given that, especially with the Ross Airstream, some of that is an effect of drainage flow and the katabatic flow in the southern portion of the Ross Ice Shelf. And so I've seen just by qualitative observation, I've seen on the satellite imagery that there are warm signatures there. Warm signatures in that region, especially going through the mountain valleys, that are most likely due to the katabatic winds. So if there's a way to calculate that, especially during a time when there's no synoptic influence, and then calculate at least the strength of the katabatic winds as the cyclone approaches, then maybe you can kind of get a before and after look at that and calculate the warming. That's
like that enhanced warming on the eastern side kind of way that you begin to see that. At least the synoptic would be right.
Yeah, I could see some of that happening, especially because you have the warm northerly flow going into the eastern Ross Ice Shelf, but also over West Antarctica. And then that flow goes down, it's forced down. So you probably get some adiabatic compression there and warming from that.
Maybe I'll dig in and ask John's question. I can't do it with his spectacular Boston accent, so you'll have to imagine it. He says, are all of these warming events preceded by notable cooling in the region as this one is? And if so, does this longer time and larger scale evolution suggest anything about teleconnections perhaps lurking in the ingredients for these events?
Not all of these regional warming events, so I'm not sure if all of these regional warming events are preceded by these large cold pools over the Ross Ice Shelf anyways. I have seen warming events that have happened in certain locations on the Ross Ice Shelf, but not others. I've seen, and especially there's a lot of warming events that happen at the southern end of the Ross Ice Shelf, near where the Ross Airstream originates. And so there could be some effect of catabatic winds and adiabatic compression and warming due to that. And maybe before that happens, you have a temperature inversion that occurs just in that location. I'm not quite sure. With the large-scale connections to the synoptic environment, or large-scale influences on the synoptic environment, I think there's something there, just based on how persistent those 500 hectopascal anomalies were in the Ross Sea and the Amundsen Sea before and during the event. But there needs to be more studies on that to kind of investigate that influence. Yeah.
Yeah, my question was kind of about the catabatic winds as well, and how they're related to the McMurdo Valley. And McMurdo Valley is kind of part of Ross Ice Shelf, I'm not sure. But I think you already answered that question, and my other question was that this particular melt that happened was like pretty north of the Antarctic, like it was not further south. Do you think that it could have been further south, or like you could have such intense warming events further south, or the topography because of the mountains won't allow that, or would make it more intense?
You can have warming events happen further south, and those generally do happen for a different reason though. Usually those warming events that happen like further south and over the actual continent, as opposed to these floating ice shelves at sea level, those usually happen due to ridge building and northerly flow, poleward flow due to that. And so a lot of times with warming events over the continent, you'll see, instead of a negative correlation between temperature and pressure, you'll see mostly a slightly positive correlation. So it's not quite as one-to-one as the Ross Ice Shelf forming event like this one is, but in general, the pressures will increase as the temperature increases too. Yeah.
How often do regional warming events occur? Like, is it a common thing, or?
It's a fairly common thing in that they usually happen every winter. But it is fairly variable from year to year. So I don't have an exact like climatology classified yet for that, but generally you get at least one a year, if not several. Yeah.
Yeah, so can you go to the figure where you had all of your different stations and the temperature trends at the very beginning?
Oh, yeah. There we go.
Yeah, so I'm curious, what do you think so you can kind of see how there's like variability between the stations?
Yeah.
The temperature, I was wondering if you had any ideas or kind of suspicions on what that could be?
Well, so like the little wiggles here could just, do you mean that, or like the start time variability?
No, like there seems to be kind of like a difference in temperature from an instantaneous measurement. It kind of looks like from a given day, you know, there's
some spreads.
Yeah.
Yeah. That I think is, so these stations are spread throughout the whole Ross Ice Shelf, and in general, the stations are a little warmer, actually at the southern end and along the Transantarctic Mountains, and colder in the center of the Ross Ice Shelf. That's just from a climatological perspective. For these actual days, it could be that you just had a little bit of temperature variation spanning across the ice shelf, and so it might be 5 degrees Celsius warmer on the northern portion on that day, and then a little cooler further south.
Do you know which stations your Calypso track went over? Your Calypso CloudSat track went over?
Yeah, I don't know exactly which ones. We could kind of like do it by eye, but I don't have that exact information. Also, I think I forgot to mention, but the Ross Ice Shelf is about the size of France, so it's pretty big. I should have said that 40 minutes ago.
What are those vertical lines on there? Is that like start and end times?
Yes,
Stations?
yeah. The vertical lines here show the beginning and end times for each of the respective warming events. And all these are colored again by the onset of the warming. Yeah.
Do you plan on developing a climatology of warming events in more of a longer time scale perspective of these events?
Yes, I do, yeah. I hope to do that for different regions of the continent as well. So, yeah, as many years as I can, and probably look at the automatic weather station data, and then catalog it for Ross Ice Shelf, West Antarctica, East Antarctica. Yeah.
Going along with that and kind of tying into John's question, it'd be interesting to see if you can get a longer historical record of these events, how does it match up with the teleconnector?
Mm-hmm.
I'd be interested personally in seeing if there's connections between the forward shift for the southern annual mode and annual
Yeah, I can see, yeah. Annual mode. Yeah.
and seeing if these events are occurring more often since we can get
Yeah, I agree. That's one thing that needs to be done in order to try to understand whether these teleconnections happen. Get a longer time record of when these warming events occur, because some of these teleconnections you need, they happen on such long time scales, and these warming events happen on such short time scales that it's really hard to confidently connect them together. But it could be that you might have these teleconnections that set up a larger scale weather pattern around Antarctica that kind of like primes the environment for these events to occur. Doesn't necessarily mean that it's gonna. So I think that might be one thing that's happening here, is that you have this large scale wave train set up, and then you have these smaller scale internal dynamics going on, such as those Adelie Land cyclones that eventually maybe they'll propagate over and then lead to the warming. Yeah.
Yeah, I was wondering, do these weather stations also take precipitation measurements as well?
They do not.
Okay. We're going to ask if, like, we looked at precipitation and how the warming events affect precipitation.
Yeah. The closest we do, our stations do get to taking precipitation is we have an acoustic depth gauge, or acoustic distance gauge, so we can get the height of that sensor above the surface. And so if we look at it on July 10th and see it's 2 meters, and then we look at it on July 16th and it's 1 meter, then like, oh, I guess a meter of snow happened, but we don't know whether that's actual falling precipitation or just blowing snow accumulating. Yeah.
So on a similar note, do you have humidity or relative humidity measured, like the observed one and not the column? Because my intuition is saying that as there was a low pressure system there, and also the recent warming heat wave that happened, there was a big role of the atmospheric rivers going into there, causing the melt, or like just the warming event. So I was curious, like whether if you have the humidity there, you can see how it changed, like whether it increased and suddenly dropped.
Yeah.
And if there were warmer temperatures, it might be snow or rain, or just like, I still think it might be humidity that could actually be the reason for this.
Yeah, I bet it does play a role. We do have relative humidity on most of our stations. I didn't look at the actual moisture flux and the moisture impact of this event, but there is I'm sure there's some impact of it, and I'm sure there's definitely more moisture coming in during the event than there was before. Yeah.
I'll ask a quick question. How common are the temperature inversions? Not necessarily associated with the warming events, but just in general, since it seems to be a precursor.
Yeah, I don't know exactly how common, but I think they're pretty common. because especially in Antarctica in the winter, you don't have any solar insulation, so you're not going to get any heating there. So as soon as you start to get calm winds and a little bit of clear sky, you're going to have that long wave radiative cooling, and so that especially really close to the surface, you're going to have that inversion develop. Well, thank you.